Welcome to video number, we don't know. Um, this isn't really fitting in line with any particular spot in our chapter, so whenever you watch this, this might be at the beginning of the chapter, it might be in the middle, it might be towards the end of the chapter. So I'm just leaving it kind of open-ended, if you will. We're going to look at some special right triangles today. One of these we've already mentioned, and it is the 45, 45, 90 right triangle. We talked about this towards the beginning of the year and how it had special properties with the Pythagorean theorem. Now, one thing to note is that since a 45, 45, 90, and when I mean 45, 45, 90, I mean we have a 45-degree angle, another 45-degree angle, and a 90-degree angle. Since we have two congruent angles, the 45s, that means we must also have two sides that are congruent. And those sides are the ones that are opposite of our two congruent angles. So this side over here, and then take that angle, go to the opposite side, and this side over here. These two sides are congruent. And if we have two congruent sides, therefore we will always have an isosceles triangle. So this is one little extra thing that's true about a 45, 45, 90, is that it will always be an isosceles triangle. Now, we've done work with these before, so I'm not going to spend too much time messing with these here, but we talked about what would happen if we had right triangles, and the legs, the a and the b for the Pythagorean theorem, what if they were the same number? So we've worked on these before where we said, all right, what if we had 3 squared plus 3 squared equals c squared, and we had 9 and 9, which made 18. And so when we square rooted that, we found 9 times 2, and we got a 3 out of the square root of 9, and the 2 had to stay behind. So we saw that pattern, right, where it was just whatever the leg was is the hypotenuse times the square root of 2. So if I had 5 and 5, well, this would be 5 times the square root of 2. And if these were 8 and 8, this would be 8 square root of 2. So in general, we talked about that for any 45, 45, 90 triangle, that if we know the legs are some particular value, the hypotenuse is that same particular value times the square root of 2. So you absolutely need to write this part down. I've got one blank triangle there on your notes. This is what you need to fill in, the x, and the x root 2. We might also fill in maybe some 45s and 45s here, just so we know it really matches. Another thing we could do is, since these are matching congruent angles, we could, instead of seeing 45s, we could just see the congruent arc marks to indicate that those are the same and therefore must be 45 degrees. So let's do some practice problems with these. Now this first one, hopefully pretty easy, right? We look at the hypotenuse. It's 20 with the square root of 2. So how big are the two legs? Well, they must be the 20s, right? If we just kind of used our patterns backwards. If these were 20, then the hypotenuse would be 20 with the square root of 2. Okay, so we didn't actually have to do any math here as long as you understand and can remember the pattern. The second one now, though, now I'm giving you the hypotenuse, but it's just 20. There is no square root of 2. Oh man, what'd you just do to us here, G? Well, let's take a look at this. This is where we're going to apply the pattern. So with the pattern, I knew the legs were x and x, and the hypotenuse was x root 2. Well, I always have to give you one side. And which side did I actually give you the value of in the pattern? I gave you the x root 2 side. So I'm just going to come over here and say the x root 2 side of the pattern is equal to 20 in this case. And what I want to figure out here is what is x and what is x, so I'm going to solve for x. So I want to divide both sides by the square root of 2. And so I've got x is equal to 20 divided by the square root of 2. Perfect. Are we done? Not quite, because we mentioned before we can't leave square roots in the denominator. So we had to do this process called rationalizing the denominator, where we took whatever the square root was in the denominator and we multiplied it in a new fraction, top and bottom, so that we have these square root of 2's down on the bottom, and that makes a square root of 4, which is just 2. And then the top, we've got 20 root 2. And then we got to watch out for any simplifying. So we can take 20 divided by 2, and that's 10. And then the root 2 sticks behind. That is x. So now I can think about just substituting in x for this side and this side. So this side is 10 root 2, and this side is 10 root 2. And there's all my missing sides. All right, let's try it again with this one. Now this one's got a root 3 on the hypotenuse, but normally it's a root 2, right? So let's see how that's going to work. So again, I'm going to apply my pattern. This is x, this is x, this is the x root 2 side. I gave you the x root 2 side, so we're going to say the x root 2 side in this case is specifically 8 root 3. I'm still going to divide the root 2 over. And again, I can't have that square root in the denominator, so I'm going to rationalize. And so now on the bottom, I get 2. Square roots go away. Then on the top, I'm going to have 8, and then square root of 2 times the square root of 3 is going to be the square root of 6. All right, now can I simplify the square root of 6? No, I'm good. But I can simplify this 8 over 2. So I know that x is equal to 4 times the square root of 6. And then again, I'm just going to substitute in, and really those are my answers. This side's 4 root 6, this side's 4 root 6, and we're done. Now, the last one for the 45, 45, 90, so I'm going to let you guys try, and I gave you a little bit easier one that you can practice with, but figure out what the other two sides are. Now, the other type of pattern, which we have not discussed, involves kinda an equilateral triangle. So imagine we've got an equilateral triangle where all three sides are 10, 10, and 10. What's special angle-wise about equilateral triangles is that all three angles must also be the same. And if triangles have 180 degrees, that means each angle must end up being 60 degrees. Okay, and that will always work for equilateral triangles, no matter what the side lengths are. Whether they're 10 or 100 each, our angles are always 60, 60, 60. Now, the pattern we're about to discuss happens when we slice an equilateral triangle in half. So if I drop down a height, basically here, these two sides that are adjacent to where the height began are the same. So that means the bottom, oh, going too far here. The bottom here gets split up between 5 and 5. And my 60-degree angle also gets split up into 30 and 30. Now, the next type of triangle we are going to discuss is a 30, 60, 90 right triangle. And it's got a particular pattern. Now, we already got two of the numbers in this specific problem, not necessarily in our pattern, but I know this bottom piece has got to be 5 because it's half of the equilateral triangle, where the equilateral triangle had a side length of 10. So if this had a length of, 20, then this piece down here would be 10 because it would be half of that. So hopefully that makes sense so far. Okay, so whatever this is, this little piece down here has got to be 5. Well, how do we figure out the third side, really the height? Well, we could use the Pythagorean theorem, right? So let's call this side, I'll just call it h because that's really what it is, it's the height. So height squared plus 5 squared equals 10 squared. Height squared plus 25 equals 100. Height squared equals 75. Square root, and I can do 25 times 3. So I get 5 root 3. So now, if we were examining and focusing on these three sides, do you think you could come up with a pattern? And I think if you sat there and thought about it for a few seconds, you'd probably say, yeah, 5 is the smallest number out of all three of these. So, what if we started with this? This side, well, that 5 is still that 5, but there's a square root of 3 attached to it. And then this side over here is really just double this side of 5, the smallest side. And that's going to be our pattern for 30, 60, 90s. Okay? Now, let's see if we can apply the pattern that we think we know so far to these three examples. And again, these are not in your notes, so don't worry about it. We're just going to follow along here. So if this is 2, we said, well, this has got to be 4, right? Because this piece over here would be 2, and that whole thing would be 4 if this was an entire equilateral triangle. All right, so this piece over here, we think it's going to be 2 root 3. Now, if I did the Pythagorean theorem real quick, if I did 2 squared plus quantity 2 root 3 squared, does that really in fact equal 4 squared? Well, that's 4. This will be 4 times 3, which is 12. And this is 16. And 4 plus 12 does in fact equal 16. So the Pythagorean theorem does in fact hold with that particular pattern. So if I had 3 down here, this would have to be 6, and this would be 3 root 3. And if this was 4, this would be 4 root 3. And this would be double the 4, and it would be 8. So our pattern now. Now, here's the thing with the pattern. With the 45, 45, 90, we had two angles that were the same. So we had two sides that were the same. all three sides in a 30, 60, 90 are going to be different. So we need to use the angles as kind of a reference between, or to indicate which sides of our pattern go where. Now, remember if we think about this being a big equilateral triangle, I know it's really cruddy equilateral triangle, but the side opposite the 30-degree angle down here, kind of this half side from the whole thing, we're going to call that our x. And the hypotenuse here was really double whatever that was. So that's why I've got that the side opposite the 90-degree angle over here is double this guy. And then the side opposite the 60, this was the piece we had to use the Pythagorean theorem with. And it was always whatever that x piece was with the square root of 3. Okay, so 30 is the smallest angle, opposite of it is the smallest side. 60 is the medium angle, so opposite of it is kind of the medium side. And the 90-degree angle is the biggest angle, so opposite of it is the largest side. So now let's apply this pattern to some examples. All right, so in this one we're going to start off easy. So here's the side opposite the 30, so I'm going to call this is my x side. Side opposite the 60, this is my x root 3. And then the hypotenuse, this is my 2x. Well, which side did I give you? I gave you the x side, which means x equals 6. There's nothing to solve here. We're just going to take that 6 and go plug it in two different spots, over here and up here. So 2 times 6, that means this piece is 12. And over here, if I plug in 6 there, then I got 6 times the square root of 3 is that side. So that's just the easiest way of seeing that type of pattern, when I give you that side opposite the 30. All right, now what if I gave you the hypotenuse to start out with? Okay, this is going to be a relatively easy one again. Let's apply the pattern. Opposite the 30 is x, opposite the 60 is x root 3, hypotenuse 2x. I gave you the 2x side, so you know that 2x is equal to 14. So we divide the 2 over, and x is 7. So let's go plug it back in the other two places. Well, that side's 7, that's easy. This side is 7 root 3. Done. You're going to hope for those all day long, but you're not going to get them. So like this one now. This one, I gave you the side opposite the 60, and this is where you would expect to see a square root of 3, but I didn't give it to you. So let's apply the pattern. This one's going to be a little bit more work. So side opposite the 30 is x. Side opposite the 60, this is the x root 3 side. Hypotenuse, 2x. So here's the piece I gave you. So we're going to come over here. The x root 3 side is equal to 8. We need to solve for x. So we need to divide the square root of 3 over. And again, we got a square in the denominator, which we can't have, so we're going to have to rationalize it. So we're going to multiply top and bottom by the square root of 3. And we'll get 8 root 3 on top, and we'll get 3 on bottom. Now, can the square root of 3 simplify? No. Can 8/3 simplify? No. So this is fully simplified, and this is x. That's what we're going to go plug in over here and over here now. So this side over here, well, it's 8 root 3 over 3. Done. Now this, we're going to take 2 times 8 root 3 over 3. And now you might question, what are we really doubling in this? Am I doubling the 8 and or the root 3 and or the 3 on the bottom? Well, think about it this way. 2, if we think about it as a fraction, is really 2 over 1. And how do we multiply fractions? Straight across. So the 2 only affects the 8 here. So it's going to be 16 root 3 and then just a 3 on bottom. And that's our hypotenuse. So the numbers here look pretty gnarly, but don't worry about them. Just leave them as simplified square roots and fractions, plug them in, and it shouldn't be an issue. All right, we're going to do one more together. So let's try this guy. Again, let's put the pattern. Opposite the 30, here's x. Opposite 60, x root 3. Hypotenuse, 2x. Which side did I give you? I gave you the 2x side. So 2x is equal to 12 root 3. We'll divide the 2 over. Now here we don't have a square in the denominator. Thank you. You're welcome. But 12 divided by 2 is 6. And then we got the root 3 left over. So there's x. Let's go plug it in these other two spots. So this piece down here on the bottom, the x, well, this is 6 root 3. Easy. Now here's where people tend to make a mistake when they come in and plug it in over here. They go, all right, well, x has a root 3 in it, so I don't really have to deal with this square root of 3 that's right here. But that would be a mistake. Technically, you're going to have root 3 twice. we're going to have 6 root 3, that's x specifically, with another root 3 tagged on the end. So we have 6 times the square root of 3 times the square root of 3. So square root of 3 times the square root of 3 is the square root of 9, which is 3. And 3 times that 6 out front makes this side 18. The last problem I want you guys to try, and I gave you an easier one to work with here. I didn't give you one that's too terribly tough, but try this one out. We'll talk about these the next day in class, and then you guys can practice some more with some easier ones and again some tougher ones. So that's all for this video.